2.7 meters long, 2.7 meters wide, and nearly 0.9 meters thick. Scientists speculate that this unusual shape and orientation during atmospheric entry reduced its speed considerably, thereby minimizing ablation and preventing fragmentation upon impact. Classified scientifically as an attack site, the Hoba Meteorite belongs to a rare subgroup of iron meteorites characterized by their high nickel content and absence of clearly visible crystalline patterns known as Widmanstätten structures. Detailed analyses have confirmed its composition to be approximately 84% iron, 16% nickel, with traces of cobalt, copper, chromium, gallium, germanium, and iridium. The absence of Widmanstätten patterns indicates extremely slow cooling within the meteorite's parent asteroid, likely taking millions of years, thus preventing the formation of characteristic iron-nickel crystalline intergrowths. Geological investigations estimate that the Hoba meteorite fell to Earth roughly 80,000 years ago during the Pleistocene epoch. Its impact velocity is estimated to have been unusually low for a meteorite of its size, possibly less than 320 meters per second. This low speed can be attributed both to its large, flattened form creating significant aerodynamic drag and its entry angle being relatively shallow. As a result, instead of forming a large impact crater typical of meteorites of comparable mass, Hoba produced only a shallow depression approximately 3 meters deep upon impact, further flattened over millennia through natural erosion processes. Numerous scientific studies have utilized modern analytical techniques such as electron microscopy, mass spectrometry, and neutron activation analysis to explore Hoba's internal structure and chemical composition. These investigations have provided insights into the conditions of the early solar system, shedding light on planetary differentiation processes, the formation of iron meteorites, and the cooling histories of their parent bodies, typically asteroids formed billions of years ago. Additionally, researchers have found minor traces of iridium within the Hoba meteorite, an element rare on Earth's crust but relatively common in extraterrestrial bodies, further confirming its cosmic origin. Due to its unique scientific value, the Hoba meteorite was designated as a national monument in Namibia in 1955. Over time, protective measures have been put in place to minimize human interference and weathering processes. Today, it serves not only as a significant geological and astronomical specimen but also as an educational landmark and major tourist attraction. Ongoing scientific interest continues, as research on the Hoba meteorite contributes valuable data on the processes of planetary formation, asteroid composition, and the broader evolution of the solar system, bridging the gap between astronomical observation and geological evidence on Earth. Further scientific investigations into the Hoba meteorite have provided valuable context for understanding the origins and behavior of extraterrestrial materials entering Earth's atmosphere. Studies involving isotopic analyses, such as measuring ratios of nickel and iron isotopes, have helped scientists reconstruct the thermal history and cooling rates of iron-rich asteroids, contributing significantly to theories about early planetary formation processes. Specifically, the slow cooling rate observed in Hoba, inferred from its isotopic and structural characteristics, suggests it originated from a large, differentiated asteroid, likely part of the metallic core of a protoplanetary body, whose formation dates back approximately 4.5 billion years, shortly after the solar system itself emerged. Radiometric dating techniques, including uranium lead and potassium argon dating, applied to trace minerals in similar iron meteorites, support the estimated ages for the Hoba meteorite's formation and subsequent space journey. These studies indicate that Hoba spent billions of years orbiting the Sun before gravitational perturbations eventually redirected its trajectory toward Earth. Such research helps astronomers better understand how gravitational interactions within the asteroid belt periodically send massive objects toward Earth's orbit. Further, chemical analyses of trace elements within Hoba, such as germanium and gallium, have proven especially valuable in meteorite classification. These trace elements are used by meteoriticists to determine links between different meteorite groups, their parent bodies, and possible asteroid families. This allows scientists to map out the diverse populations of asteroids in our solar system and enhances our understanding of asteroid mining potentials, given that iron meteorites such as Hoba contain substantial amounts of rare and valuable metals. The meteorite's lack of significant deformation and its intactness upon landing have intrigued physicists studying meteorite impact mechanics. Computational modeling and wind tunnel simulations have been conducted to explain the unique conditions that led Hoba to retain its integrity. These studies have shown that its aerodynamic shape allowed it to decelerate significantly, avoiding explosive fragmentation or cratering impact. This information is crucial for predicting potential hazards from future asteroid impacts and developing planetary defense strategies, as it highlights how even large objects can enter the Earth's atmosphere without causing catastrophic impacts under specific aerodynamic and entry angle conditions. Furthermore, recent research has explored microscopic weathering processes acting on Hoba's surface. Chemical weathering and oxidation studies provide insights into how meteorites degrade when exposed to Earth's environment over thousands of years. Understanding these processes allows for improved preservation methods for meteorite samples, essential for ongoing scientific research and conservation of valuable extraterrestrial artifacts. Educationally, the Hoba Meteorite continues to inspire public interest in astronomy, geology, and planetary sciences. Its presence in Namibia has contributed significantly to local educational initiatives, raising awareness about Earth's geological history, cosmic events, and scientific careers among students and visitors. Efforts are ongoing to maintain the site for educational outreach, ensuring the meteorite's scientific significance is communicated effectively to future generations. In summary, the Hoba Meteorite remains a cornerstone of multidisciplinary scientific research, bridging astronomy, geology, physics, and planetary science. Its ongoing study provides deep insights into asteroid formation, planetary differentiation, cosmic history, and atmospheric entry phenomena, enhancing human understanding of our solar system's past and informing our preparations for potential future encounters with celestial bodies. Additionally, the scientific exploration of the Hoba meteorite has broader implications for understanding the cosmic distribution of rare metals and the potential for asteroid mining. Iron meteorites, such as Hoba, are particularly rich in economically valuable metals, including nickel, cobalt, platinum group elements, PGEs, iridium, and palladium. Detailed spectroscopic and chemical analyses conducted on Hoba and similar iron meteorites provide baseline data useful in evaluating asteroids as potential sources of strategic minerals. Such data supports growing scientific and commercial interest in asteroid exploration and resource utilization, guiding missions aimed at sustainably harnessing extraterrestrial materials. Furthermore, studies involving the Hoba meteorite have also assisted in calibrating analytical instruments used in planetary exploration. The meteorite's stable, well-characterized chemical and isotopic composition makes it an ideal reference standard for instruments like mass spectrometers, electron microscopes, X-ray diffraction devices, and gamma-ray spectrometers, equipment regularly deployed in space missions to Mars, asteroids, and comets. Thus, Hoba indirectly aids the accurate interpretation of remote sensing and analytical data collected from spacecraft, enhancing the scientific return of space exploration programs. Astrobiological implications of the Hoba meteorite and iron meteorites, in general, have also captured researchers' attention. Although Hoba itself lacks organic molecules or evidence of life, iron meteorites contribute valuable insights into planetary protection and contamination studies. Understanding how meteorites weather on Earth, how quickly extraterrestrial materials degrade, and how iron-rich environments interact chemically and biologically upon arrival helps planetary scientists develop accurate models for planetary protection, particularly concerning future Mars sample return missions and the safe handling of extraterrestrial samples. Moreover, the site surrounding the Hoba meteorite has attracted geological and environmental research. Investigations into local soil chemistry, vegetation growth patterns, and microbial communities near the meteorite have provided valuable insights into how extraterrestrial metallic objects interact with Earth's biosphere and geosphere over long timescales. These interdisciplinary studies offer valuable reference points for astrobiologists studying analogous processes that might occur on other planets or moons after meteorite impacts. Scientific outreach programs centered around the Hoba meteorite also reinforce public understanding of meteorites as significant natural history artifacts. International collaborations, scientific symposiums, and educational tours organized at the Hoba site further highlight the importance of preserving scientifically valuable geological landmarks. Such efforts strengthen public appreciation for meteorite science, motivating support for ongoing meteorite recovery in research programs worldwide. In conclusion, the continued investigation and conservation of the Hoba meteorite offer invaluable opportunities for multidisciplinary scientific advancement. From improving our understanding of planetary formation and asteroid impacts to guiding practical applications in planetary defense and space resource utilization, Hoba remains an essential focal point of research in planetary science, geology, chemistry, astrobiology, and space exploration. Further research into the Hoba meteorite has also contributed significantly to planetary defense studies, particularly in developing more accurate predictive models of meteorite behavior during atmospheric entry. Scientists employ computer simulations, incorporating Hoba's unique physical characteristics, to refine atmospheric trajectory calculations, impact prediction methods, and disaster preparedness strategies. Such predictive models assist international scientific communities and governmental agencies in assessing potential threats posed by near-Earth objects, NEOs, and designing effective mitigation approaches. The geochemical composition of the Hoba meteorite, specifically its elevated nickel content, provides critical clues into the formation processes of metallic planetary cores. Comparative analyses between iron meteorites like Hoba and seismic data from Earth's core help researchers better interpret Earth's internal structure, thermal history, and core mantle interactions. These analogies expand knowledge of planetary differentiation, a vital geological process determining the layered internal structures common among terrestrial planets, including Mercury, Venus, Earth, and Mars. Additionally, the corrosion and weathering studies of the Hoba meteorite offer a unique opportunity to observe how iron-rich extraterrestrial materials interact over time with Earth's atmospheric and environmental conditions. Detailed analyses reveal the progressive formation of iron oxide minerals such as magnetite, hematite, and goethite on Hoba's surface, demonstrating oxidation processes at varying depths and conditions. This information allows researchers to reconstruct past climate conditions and environmental histories of the region, linking meteoritic studies directly to Earth's climatological research. From an educational standpoint, the ongoing scientific interest in Hoba has encouraged numerous collaborative international projects, promoting meteorite science education globally. Institutions worldwide frequently reference Hoba in developing educational curricula, outreach programs, and museum exhibits, significantly influencing public understanding and appreciation of astronomy and geology. Such international recognition fosters scientific cooperation, encourages student involvement in meteoritics, and increases public support for ongoing space science research. The discovery and detailed study of the Hoba meteorite have also inspired advances in laboratory methodologies for extraterrestrial materials. Advanced analytical techniques, including synchrotron radiation spectroscopy, laser ablation inductively coupled plasma mass spectrometry, LAICPMS, and high-resolution electron microscopy, have been refined through analyses of Hoba-like materials. These advancements not only deepen scientific knowledge about the meteorite itself but also broadly enhance research capabilities applicable across multiple scientific disciplines. Finally, ongoing efforts to preserve the Hoba meteorite site underscore the importance of conservation measures in safeguarding rare geological and astronomical heritage. Recognizing its scientific, cultural, and historical value, conservationists, scientists, and local authorities have collaborated on protective strategies aimed at minimizing vandalism, natural erosion, and anthropogenic impacts. These preservation efforts set an important international precedent, highlighting the need for protecting scientifically significant meteorite sites around the world, thus enabling continued scientific access and public education for generations to come. In essence, the comprehensive exploration and preservation of the Hoba Meteorite offer profound and wide-ranging implications across diverse scientific fields: planetary science, astronomy, geology, geochemistry, climatology, planetary defense, and astrobiology, making it not only the largest meteorite on Earth, but also one of the most scientifically influential extraterrestrial objects ever discovered. The Hoba meteorite continues to serve as a cornerstone for interdisciplinary scientific research, providing valuable data on planetary formation, impact physics, space resources, and terrestrial environmental interactions. While its sheer size and composition make it an extraordinary object of study, ongoing investigations have expanded its relevance to emerging fields such as space mining, planetary habitability, and long-term preservation of extraterrestrial materials. One of the critical areas of study involving the Hoba meteorite is its planetary core formation theories. Scientists hypothesize that iron meteorites like Hoba originate from the metallic cores of differentiated asteroids that were shattered in early solar system collisions. By examining the metallurgical properties and isotopic compositions of Hoba and other iron meteorites, researchers can infer how molten iron-nickel alloys crystallized within protoplanets billions of years ago. The high concentration of nickel and trace elements like iridium and platinum in Hoba supports models suggesting that such metallic bodies experienced slow cooling within large parent asteroids, similar to Earth's core formation processes. Beyond geological and planetary sciences, Hoba has influenced the growing field of planetary defense. While its low-velocity impact minimize destruction, its size and mass highlight the potential risks associated with larger asteroids. By comparing the structure and atmospheric entry characteristics of Hoba with other impact events, such as the 1908 Tunguska event and the 2013 Chelyabinsk meteor, scientists have refined impact risk assessments. The study of Hoba provides insight into how different entry angles, velocities, and compositions influence an object's survivability upon reaching the Earth's surface. Hoba's unique preservation has also contributed to ongoing research in space weathering. Unlike most iron meteorites, which rapidly oxidize and degrade when exposed to Earth's atmosphere, Hoba has remained relatively well preserved despite being exposed for thousands of years. Scientists attribute this to a combination of factors, including its chemical composition, the regional climate of Namibia, and natural protective patina layers forming on its surface. The study of this weathering process helps researchers understand the longevity of metallic structures in space, with implications for the preservation of spacecraft, satellites, and lunar or Martian exploration equipment exposed to harsh extraterrestrial environments. Another emerging research field related to Hoba involves the study of microbial interactions with meteoritic materials. Scientists have discovered that iron-oxidizing bacteria colonize meteorites over time, influencing their weathering patterns. Similar microbial processes could play a role in extraterrestrial environments such as Mars, where iron-rich meteorites have been found on the planet's surface. These studies contribute to astrobiology by offering analogs for potential microbial life processes on Mars and other celestial bodies, furthering the search for life beyond Earth. Additionally, the Hoba Meteorite has reinforced discussions on asteroid mining and space resource utilization. With the growing interest in extracting metals from space, particularly from near-Earth asteroids, Hoba serves as a natural laboratory for understanding the composition, structural integrity, and potential economic value of iron-nickel meteorites. Scientific advancements made through studying Hoba contribute to the technological development of future asteroid mining missions, which could provide critical resources for deep space exploration and reduce humanity's dependence on Earth-bound metal resources. The Hoba meteorite's importance extends beyond pure scientific inquiry. It plays a vital role in public education and cultural significance. Museums, universities, and educational institutions worldwide incorporate Hoba's findings into their research programs, lectures, and exhibitions, fostering a greater appreciation for planetary science among students and the general public. The Namibian government and scientific organizations continue to invest in site conservation, ensuring that Hoba remains both a scientific and cultural landmark. As research methodologies evolve and space exploration progresses, the Hoba Meteorite Meteorite will continue to provide new insights into planetary formation, impact science, and space resource utilization. Its legacy as the largest intact meteorite on Earth will undoubtedly influence future generations of scientists, engineers, and space explorers, reinforcing its position as one of the most scientifically valuable extraterrestrial objects ever discovered. As scientific advancements continue, the Hoba meteorite is a valuable subject for further research, particularly in space science, planetary defense, and material science. Modern analytical techniques, including synchrotron X-ray diffraction, laser-induced breakdown spectroscopy, LIBS, and neutron activation analysis, are increasingly being applied to iron meteorites, allowing researchers to probe their atomic structure and elemental composition at unprecedented resolutions. Future studies of Hoba could provide deeper insights into the physical and chemical conditions under which iron meteorites form and evolve in space. Hoba's composition closely resembles that of Earth's outer core, making it a useful analog for studying planetary interiors. Recent advances in high-pressure physics have enabled scientists to recreate core-like conditions in laboratory settings, using diamond anvil cells and shock-wave experiments. By analyzing how Hoba's iron-nickel alloys behave under extreme temperatures and pressures, researchers can refine models of planetary core differentiation and magnetic field generation, particularly for terrestrial planets like Mars, which may have once had a magnetic dynamo, but lost it over time. Additionally, studies of the residual magnetism in iron meteorites help reconstruct past magnetic fields of their parent asteroids. Hoba's structure could retain information about the magnetic environment in which it formed billions of years ago. Such studies provide critical data on the evolution of early planetary bodies, helping to determine how magnetic fields influence the development of atmospheres and the potential habitability of exoplanets. With growing concerns over near-Earth objects, NEOs, and potential asteroid impact threats, the study of large iron meteorites like Hoba remains crucial for planetary defense strategies. Unlike stony meteorites, which often fragment upon entry, iron meteorites tend to remain intact, posing a greater risk of reaching the ground with significant kinetic energy. The Hoba meteorite's unusually flat shape and low impact velocity suggest that certain geometries may reduce the likelihood of high-energy crater formation. Computational fluid dynamics (CFD) simulations and wind tunnel experiments using scaled detailed iron models based on Hoba's dimensions could help refine impact predictions for future meteorite encounters. Understanding how different meteorite compositions and shapes influence atmospheric deceleration, fragmentation, and ground penetration will be essential for designing asteroid deflection missions, such as those tested in NASA's Double Asteroid Redirection Test (DART), and upcoming European Space Agency (ESA) projects. Hoba serves as a natural model for space mining technologies, particularly for refining iron-rich asteroids. With increasing global interest in utilizing asteroid resources for deep space exploration, the metallurgy of iron meteorites is being studied for potential in situ resource utilization (ISRU). The high nickel content of Hoba is particularly valuable, as nickel alloys are critical for aerospace engineering and radiation shielding in long-duration space missions. By studying the microstructure and crystallization of Hoba's iron-nickel phases, metallurgists and materials scientists can better understand how to extract and process metals in low-gravity environments. Future robotic mining missions to metallic asteroids, such as NASA's Psyche mission, will benefit from detailed knowledge gained from iron meteorites like Hoba. Understanding how to efficiently cut, shape, and refine meteoritic metal without the use of oxygen-dependent processes, such as traditional smelting, is an ongoing challenge that space mining researchers are actively addressing. Despite exposure to Earth's atmosphere for thousands of years, Hoba has remained relatively intact compared to other iron meteorites, which often deteriorate rapidly due to oxidation. This makes Hoba an ideal case study for understanding corrosion resistance in extreme environments. Metallurgists and materials engineers are examining its naturally formed oxide layers to develop more durable coatings and surface treatments for spacecraft, satellites, and structures exposed to harsh conditions. By replicating Hoba's weathering processes in controlled laboratory settings, scientists can create advanced corrosion-resistant materials for aerospace applications, particularly for long-duration missions to the Moon and Mars, where metallic structures will be exposed to regolith dust, solar radiation, and extreme temperature fluctuations. This research has broader applications on Earth, potentially improving the longevity of steel and iron structures in marine and industrial environments. Recent discoveries of microbial life forms that interact with meteoritic material have opened new avenues for research into biogeochemistry and astrobiology. Iron oxidizing bacteria and extremophilic microbes are known to colonize meteorites, influencing their weathering rates and chemical transformations. Studying how microbial communities interact with the iron-rich surface of Hoba may provide insights into potential extraterrestrial microbial life, particularly on Mars, where meteorites serve as natural reservoirs of iron and other essential nutrients. Geochemical analyses of Hoba's trace elements, particularly iridium and platinum group metals, could also contribute to studies on mass extinctions and impact events. The presence of high iridium concentrations in geological layers is often used as evidence of past asteroid impacts, such as the Chicxulub impact, which contributed to the extinction of the dinosaurs. By comparing Hoba's chemical profile to impact-generated deposits, scientists can refine impact dating techniques and improve models of how asteroid collisions influence planetary evolution. Beyond its scientific significance, Hoba remains a major cultural and educational landmark. The Namibian government and international conservation organizations continue efforts to protect the site from human-induced damage and environmental degradation. Ongoing site management strategies include controlled visitor access, protective coatings to prevent further oxidation, and digital archiving of high-resolution 3D scans for scientific documentation. Efforts are also being made to incorporate Hoba into international meteorite research networks, allowing scientists worldwide to compare its properties with other large iron meteorites such as the Cape York meteorite, Greenland, the Willamette meteorite, USA, and the Gibeon meteorite, Namibia. These collaborations facilitate a broader understanding of meteoritic diversity and contribute to planetary science research initiatives, including NASA and ESA programs on planetary material studies. In conclusion, the Hoba meteorite remains one of Earth's most valuable extraterrestrial objects, with implications spanning planetary science, space exploration, material science, and astrobiology. Its unique physical and chemical properties continue to provide a wealth of information that informs not only our understanding of past cosmic events, but also our preparation for future challenges in space exploration and planetary defense. As technology advances, new discoveries discoveries about Hoba and its broader scientific applications will likely emerge, ensuring that this remarkable meteorite remains at the forefront of planetary science for generations to come. The ongoing study of the Hoba meteorite continues to contribute to cutting-edge developments in planetary science, engineering, and space exploration. As new technologies emerge, the scientific community is increasingly looking to meteorites like Hoba to provide answers to fundamental questions about the early solar system, asteroid composition, and the long-term impact of extraterrestrial materials on Earth's geology and biosphere. Several promising research avenues and applications are currently under consideration. One of the most intriguing aspects of Hoba's composition is its high nickel content, which makes it an excellent model for studying advanced alloys used in aerospace engineering. Nickel-iron alloys are widely utilized in spacecraft design due to their exceptional strength, resistance to corrosion, and ability to withstand extreme temperatures. The study of Hoba's microstructure, particularly its crystalline arrangement, can provide insights into how natural iron-nickel alloys behave under extreme conditions. This knowledge is crucial for improving heat shields, re-entry vehicles, and next-generation spacecraft capable of surviving deep space radiation and high-temperature fluctuations. With increasing interest in lunar and Martian colonization, in situ resource utilization, ISRU, is becoming a priority for space agencies. Given the abundance of metallic asteroids, research inspired by Hoba's metallurgical properties could lead to the development of space-based 3D printing techniques that use metal-rich asteroids to construct durable structures on the Moon or Mars. Such technology would reduce reliance on Earth-based materials, making long-duration space missions more feasible. Meteorites like Hoba serve as natural laboratories for understanding the processes that shaped rocky planets, both in our solar system and beyond. By analyzing the isotopic composition of Hoba, scientists can make comparisons with meteorites found on Mars and asteroids such as Vesta and Psyche. The study of iron meteorites is crucial for understanding the differentiation of planetary bodies, how they formed metal-rich cores and silicate mantles. If iron meteorites like Hoba originated from the shattered cores of early protoplanets, similar processes may be occurring in distant exoplanetary systems. This could help scientists refine their models of planet formation and better predict the internal compositions of exoplanets detected via telescopes like James Webb Space Telescope, JWST, and upcoming missions such as Plato and Ariel. Hoba's long exposure to Earth's environment provides a case study for understanding how iron-rich materials degrade over time. Similar processes may occur on the Moon, Mars, and even icy moons such as Europa and Titan, where surface chemistry is influenced by cosmic radiation, temperature fluctuations, and potential interactions with liquid environments. Future planetary missions could analyze meteoritic weathering on Mars to compare it with terrestrial samples like Hoba. Although the Hoba meteorite itself does not contain organic compounds, iron meteorites have been proposed as potential catalysts for prebiotic chemistry, the processes that led to the formation of life on Earth. The interaction of meteoritic iron with early Earth's atmosphere and hydrosphere could have played a role in the synthesis of essential biomolecules. Iron and nickel catalyze many biochemical reactions essential for life. Some researchers propose that iron meteorites delivered crucial elements to early Earth, potentially acting as natural reactors for the formation of amino acids and other organic compounds. Experiments simulating early Earth conditions have demonstrated that metal-rich meteorites could have facilitated the synthesis of complex molecules in primordial oceans. Recent discoveries of extremophilic microorganisms capable of metabolizing iron suggest that similar microbial communities could have existed on early Mars or even in subsurface oceans of Europa and Enceladus. Studying microbial colonization of meteorites like Hoba may provide insights into potential biosignatures that future space missions should look for when searching for extraterrestrial life. Due to its importance in scientific research, the Hoba meteorite is subject to preservation efforts to prevent further degradation. The exposure of iron meteorites to Earth's humid climate and biological activity leads to gradual oxidation and surface alteration. Scientists are developing protective coatings and controlled environmental conditions to slow these processes and ensure long-term scientific access. One of the most significant advancements in meteorite conservation is high-resolution 3D scanning technology. Scientists have created digital replicas of the Hoba meteorite using LiDAR and photogrammetry, allowing researchers worldwide to study its structure remotely. This also enables future comparative studies with other meteorites and impact structures. Hoba remains an important cultural and scientific monument, attracting thousands of visitors each year. Scientific outreach programs, museum exhibitions, and virtual reality simulations allow students and the general public to explore the significance of meteorites in planetary science. Organizations like NASA, ESA, and the Namibian government collaborate on educational initiatives to increase awareness of meteorite science and space exploration. The continued study of Hoba will likely contribute to upcoming space missions designed to explore metallic asteroids and planetary interiors. Several proposed missions may benefit from insights gained from meteorites like Hoba. NASA's Psyche mission, 2026. This mission aims to explore the metal-rich asteroid Psyche, believed to be the exposed core of an early protoplanet. Hoba's composition will provide a reference point for understanding Psyche's surface material and metallic evolution. ESA's Hera mission, 2027, part of planetary defense initiatives. Hera will analyze the internal structure of asteroid Didymos and its moonlet Dimorphos, which was impacted by NASA's DART mission. Understanding iron meteorites like Hoba helps refine models of asteroid impact dynamics. Lunar and Martian resource utilization missions. Future Artemis and Mars exploration missions will study in situ resource utilization, ISRU, for metal extraction, using meteorite data to guide material selection and processing techniques for building infrastructure on other planets. The Hoba meteorite is far more than just the largest meteorite ever discovered. It is a key to understanding the history of the solar system, planetary differentiation, impact mechanics, and even the potential for extraterrestrial life. Its continued scientific relevance spans numerous disciplines, from geochemistry and astrobiology to planetary defense and space mining. As technology advances, new discoveries related to Hoba's structure, composition, and history will continue to shape our understanding of the cosmos. Whether through aiding spacecraft material development, refining planetary formation theories, or contributing to space resource utilization, Hoba remains a foundational object of study in planetary science. Future generations of scientists, engineers, and space explorers will undoubtedly return to the lessons learned from Hoba as they venture further into the unknown realms of space. The meteorite's enduring legacy ensures that its contributions to science and exploration will remain significant for centuries to come. As space exploration continues to evolve, the significance of the Hoba meteorite extends far beyond its status as the largest known meteorite on Earth. Its physical and chemical characteristics make it a crucial reference point for various scientific fields, including planetary geology, space mining, impact physics, and extraterrestrial resource utilization. Researchers continue to leverage Hoba's unique properties to enhance our understanding of planetary formation, asteroid impact mitigation, and the potential for interplanetary colonization. One of the most promising applications of Hoba's study is its role as a terrestrial analog for metallic asteroids. As private companies and space agencies ramp up efforts to explore and extract valuable resources from asteroids. Iron-nickel meteorites, like Hoba, serve as natural case studies for understanding the mining potential of metal-rich celestial bodies. Space agencies such as NASA, ESA, and private companies like SpaceX and Blue Origin are exploring asteroid mining as a long-term solution to resource shortages on Earth. The composition and structure of Hoba closely resembled that of asteroid 16 Psyche, a metal-rich body in the asteroid belt believed to be the exposed core of an early planetary embryo. NASA's Psyche mission, launching in 2026, aims to study this asteroid's surface composition, structure, and potential mining viability. Data from Hoba has already influenced the mission's scientific objectives, providing baseline measurements for metallic asteroid compositions. Engineers studying the metallurgy of Hoba and similar meteorites are using this data to design automated drilling, refining, and metal extraction systems for future asteroid mining missions. Understanding how natural iron-nickel alloys behave in extraterrestrial environments will aid in the development of mining equipment that can operate in low gravity, high radiation conditions without relying on Earth-based infrastructure. One of the biggest concerns for space agencies is the potential threat posed by near-Earth objects, NEOs. While small meteoroids frequently burn up in Earth's atmosphere, larger bodies, especially iron meteorites like Hoba, have the potential to cause significant damage if they reach the surface. Studying Hoba's impact dynamics provides valuable insights into planetary defense strategies. Hoba's mass, shape, and structural integrity offer a real-world case study for low-velocity atmospheric entry scenarios. Unlike stony meteorites, which tend to fragment upon entry, iron meteorites like Hoba have a higher probability of reaching the ground intact. Using computational fluid dynamics (CFD) models, scientists are simulating potential impact scenarios for iron-rich asteroids, helping to refine predictions of impact zones, fragmentation patterns, and energy dissipation. The data gathered from Hoba and similar meteorites is influencing planetary defense initiatives such as the NASA DART Double Asteroid Redirection Test mission, which successfully altered the orbit of an asteroid by impacting it with a kinetic projectile. The European Space Agency's Terra mission, 2027, will follow up on DART's results, studying how iron-rich bodies respond to impact forces. Hoba provides an important comparative dataset, helping scientists determine whether similar deflection methods could be used for larger metallic asteroids. Meteorites like Hoba provide direct evidence of the processes that shape the metallic cores of rocky planets. Exoplanet research increasingly relies on iron meteorite studies to model the interiors of distant worlds. Iron meteorites are thought to originate from the shattered cores of ancient protoplanets that once existed in the early solar system. Hoba's composition closely matches that of Earth's and Mars' metallic cores, suggesting that similar differentiation processes occurred across multiple planetary bodies. Studying how Hoba's nickel-iron structure formed provides insights into the internal differentiation of exoplanets, including those in the habitable zones of other star systems. The presence or absence of a strong planetary magnetic field can influence a planet's ability to sustain life by shielding its atmosphere from solar and cosmic radiation. Iron-rich planetary cores generate these fields through convection processes. By examining the trace magnetic properties of Hoba, scientists can infer how metallic cores behave over time, helping refine models of magnetic field evolution for exoplanets. The intersection of meteoritics and astrobiology is an emerging field, and Hoba's composition makes it a valuable subject of study in this context. Some scientists propose that iron meteorites may have played a role in the origin of life on Earth by acting as catalysts for biochemical reactions. Experiments have demonstrated that iron-nickel meteorites, when exposed to early Earth conditions, can facilitate the formation of amino acids and organic molecules. Since iron is an essential element in biological processes, large meteorites like Hoba could have seeded early Earth's oceans with essential building blocks for life. Microbiologists have also studied microbial life that thrives on iron-rich surfaces. Iron-oxidizing bacteria have been found on meteorites, leading to speculation that similar life forms could exist on Mars, where iron-rich meteorites have been discovered on the surface. The microbial communities that interact with Hoba may provide insights into potential biosignatures that future Mars rovers and sample return missions should look for. As one of the most famous meteorites in the world, Hoba is an essential cultural and scientific landmark. Efforts are underway to ensure its long-term preservation and accessibility for scientific research. Despite its impressive size, Hoba is vulnerable to oxidation and weathering. Scientists are exploring various methods to prevent further corrosion, including applying protective coatings, interactions, and implementing climate-controlled enclosures. This research could also inform preservation techniques for future lunar and Martian exploration sites, where iron-rich materials may degrade in unique ways due to different atmospheric conditions. Hoba is a scientific artifact. It is a major educational resource. Researchers are working to digitize the meteorite using high-resolution 3D scanning, allowing virtual exploration for students and scientists worldwide. Museums, universities, and online platforms are incorporating virtual reality (VR) and augmented reality (AR) applications to bring Hoba's history and scientific significance to a broader audience. The Hoba meteorite remains one of the most scientifically significant extraterrestrial objects on Earth. Its study continues to shape our understanding of planetary formation, core differentiation, asteroid impact dynamics, and planetary deep mining and resource utilization, astrobiology, and the origins of life, exoplanetary geology, and habitability. As scientific methodologies advance, Hoba will undoubtedly play an even greater role in planetary science, materials engineering, and space exploration. Its continued research will not only expand our knowledge of the past but also help prepare for humanity's future beyond Earth, from asteroid mining and planetary colonization to the search for life in the universe. With its unique combination of history, geology, and astronomy, Hoba stands as a testament to both Earth's cosmic heritage and the limitless potential of human exploration. As research on the Hoba meteorite progresses, its impact extends beyond planetary science into new and emerging fields, including artificial intelligence-assisted mineral analysis, deep space metallurgy, and comparative planetology. Scientists continue to explore innovative ways to extract knowledge from Hoba, applying its lessons to modern space exploration and Earth-based scientific advancements. With advances in artificial intelligence, AI, and machine learning, ML, researchers are now able to conduct more detailed and precise analyses of meteorites like Hoba. AI-driven spectroscopy and deep learning algorithms can detect subtle variations in meteorite composition that were previously unnoticed, improving classification techniques and refining our understanding of how iron meteorites form and evolve. Using hyperspectral imaging combined with AI, scientists can identify the exact mineral phases present in Hoba without damaging the specimen. This technique allows for non-invasive analysis, preserving the meteorite while still extracting valuable data on its elemental distribution, trace minerals, and weathering effects. By training AI models with data from meteorites like Hoba, planetary scientists can better predict the composition of unexplored asteroids. Space agencies are using these models to improve asteroid mining strategies, target selection for future missions, and risk assessments for potentially hazardous asteroids. Hoba provides valuable data for metallurgy research in space, influencing how future space colonies might extract and process metals from asteroids and planetary surfaces. One of the biggest challenges in space mining is the efficient extraction and refining of metals in a microgravity environment. By studying how the iron-nickel alloys of Hoba formed and cooled in space before impact, researchers can develop smelting and 3D printing technologies for use on the Moon, Mars, and beyond. The Hoba meteorite remains one of the most remarkable extraterrestrial objects ever discovered, with a scientific, historical, and cultural significance that continues to grow. Its immense size, unique composition, and preservation have provided researchers with invaluable insights into planetary formation, impact physics, and the chemical evolution of metal-rich bodies in space. As technological advancements refine our ability to study meteorites at microscopic and atomic scales, Hoba serves as a crucial reference point for understanding the processes that shaped the early solar system. Beyond its role in planetary science, the meteorite has contributed to advancements in metallurgy, space mining, and planetary defense strategies. As humanity looks toward long-term space exploration and settlement, the study of iron meteorites like Hoba offers practical applications for extracting and utilizing resources beyond Earth. The knowledge gained from its structure and elemental composition aids in the design of future spacecraft, habitat construction on the Moon and Mars, and the refinement of materials that must withstand extreme space environments. Hoba's significance extends beyond academia, serving as a bridge between scientific discovery and public engagement. Most visited meteorite sites in the world, it continues to inspire curiosity and wonder about the cosmos, connecting people with the broader story of Earth's interactions with space. Conservation efforts ensure that future generations will have the opportunity to study and appreciate this natural wonder, preserving it as both a scientific resource and a cultural landmark. As research continues, new discoveries will further expand our understanding of Hoba's origin, its journey through space, and its impact on Earth. Whether through planetary geology, exoplanetary science, or the quest to understand the building blocks of life, this meteorite remains a silent witness to billions of years of cosmic history. Its presence on Earth is not only a reminder of our planet's dynamic relationship with the universe, but also a testament to the enduring quest for knowledge that drives scientific exploration forward. The largest meteorite ever discovered on Earth is the Hoba Meteorite, located named after the West Farm where it was found. It is notable not only for its massive size, but also because it remains in its original landing position, as it was too heavy to move after discovery. Weighing approximately 60 metric tons, is classified as an attack site, a rare type of iron meteorite primarily composed of iron, around 84%, and nickel approximately 16%, along with trace amounts of cobalt and other elements. It measures roughly 2.7 meters in length, 2.7 meters in width, and nearly 0.9 meters in thickness, featuring a uniquely flat rectangular shape uncommon among meteorites, which are typically more irregular and rounded due to atmospheric entry erosion. Scientific estimates indicate that the Hoba meteorite fell to Earth approximately 80,000 years ago. Its velocity upon impact, preventing the formation of a significant crater. Instead, the meteorite merely created a shallow depression, and erosion has further minimized evidence of its impact over thousands of years. Today, the Hoba Meteorite is preserved at the site of its original discovery, serving as both the scientific landmark and a major tourist attraction. Its exceptional preservation and enormous size make it a valuable resource for researchers studying planetary formation, metallurgy, and cosmic events, offering unique insights into the history of our solar system and the nature of cosmic meteorite ever discovered on Earth is the Hoba Meteorite, situated near Namibia. First discovered roughly 2.7 meters long, 2.7 meters wide, and nearly 0.9 meters thick. Unusual shape and orientation during atmospheric entry reduced its speed considerably, thereby minimizing ablation and preventing fragmentation upon impact. Classified scientifically as an attack site, the Hoba Meteorite belongs to a rare subgroup of iron meteorites characterized by their high nickel content and absence of clearly visible patterns known as Whitman structures. Detailed analyses have confirmed its composition to be approximately 84% iron, 16% nickel, with traces of cobalt less than 320 meters per second. This low speed can be attributed both to its large, flat aerodynamic drag in its entry angle being relatively shallow. As a result, instead of forming a large impact crater typical of meteorites of comparable mass, Hoba produced only a shallow depression approximately 3 meters deep upon impact, further flattened over millennia through natural erosion processes. Numerous scientific studies have utilized modern analytical techniques such as electron microscopy, mass spectrometry, and activation analysis light on planetary differentiation processes, the formation of iron meteorites, and the cooling histories of their parent bodies. Typically, billions of years ago. Rare on Earth's crust, but relatively common in extraterrestrial bodies, further confirming its origin. Due to its unique value, meteorite was designated as a national monument in Namibia in 1955. Over time, protective measures have been put in place to minimize human interference and weathering processes. Today, it serves not only as a geological and astronomical specimen, but also as an educational landmark and major tourist attraction. Ongoing scientific interest continues as research on the Hoba Meteorite contributes valuable data on the processes of planetary formation, asteroid composition, and the Context the studies involving isotopic reconstruct the thermal history and cooling rates of iron-rich asteroids, contributing significantly to theories about early formation processes. Specifically, the slow cooling rate observed in Hoba inferred from its isotopic and structural characteristics originated from a large differentiated asteroid, likely part of the metallic core of a These studies indicate that Hoba trajectory toward Earth. Understand how gravitational interactions within the asteroid belt send massive objects toward Earth's orbit. Chemical analyses of trace elements within Hoba, such as germanium and gallium, have proven especially valuable in meteorite classification. These trace elements are used by meteoriticists to determine links between different meteorite groups, their parent bodies, and possible asteroid families. This allows scientists to map out the diverse populations of asteroids in our solar system and enhances our understanding of asteroid mining potentials, given that iron meteorites such as Hoba contain substantial amounts of rare and valuable metals. The meteorite's lack of significant scientists studying meteorite impact computational modeling and wind tunnel simulations have been conducted to explain the unique conditions that led Hoba to retain its integrity. These studies have shown that its aerodynamic shape allowed it to decelerate significantly, avoiding explosive fragmentation or cratering impact. This information is crucial for predicting potential hazards from future impacts and developing planetary defense strategies, as it highlights how even large objects can enter the Earth's atmosphere without causing catastrophic impacts under specific aerodynamic and entry angle conditions. Furthermore, recent research has explored microscopic weathering processes acting on Hoba's surface. Chemical weathering oxidation studies provide insights into how meteorites degrade when exposed to Earth's environment over thousands of years. Understanding these processes allows for improved preservation methods for meteorite samples, essential for ongoing scientific observation of valuable extraterrestrial artifacts. Educationally, the Hoba Meteorite continues to inspire public interest in astronomy, geology, and planetary science. Its presence in Namibia has contributed significantly to local educational initiatives, raising awareness about Earth's geological history, cosmic events, and scientific careers among students and visitors. Ensuring the meteorite's scientific significance is communicated effectively to future generations. Atmospheric broad in asteroid exploration and resource utilization, guiding missions aimed at sustainably harnessing assisted in calibrating analytical instruments used in planetary exploration. The meteorite's stable, well-characterized chemical and isotopic composition makes it an ideal reference standard for instruments like mass spectrometers, electron microscopy, gamma ray spectrometers, deployed in Mars asteroids, and comets. Hoba indirectly aids the accurate interpretation of remote sensing and analytical data collected from spacecraft, enhancing the scientific return of space exploration programs. Astrobiological implications of the Hoba meteorite and iron meteorite involves although Hoba itself lacks organic molecules or evidence of life, iron meteorites contribute valuable insights into planetary protection and contamination and how rich chemically biologically upon arrival helps planetary scientists develop accurate models for planetary protection, particularly concerning future Mars sample return missions and the safe handling of extraterrestrial samples. Moreover, the site surrounding the Hoba meteorite has attracted geological and investigations into local soil chemistry, vegetation growth patterns, and microbial communities near the meteorite have provided valuable insights into how extraterrestrial metallic objects interact with Earth's biosphere and geosphere over long time scales. These interdisciplinary studies offer valuable reference point biologists studying analogous processes that might occur on other planets or moons after meteorite impacts. natural history artifacts. International collaborations, scientific symposiums, and educational site further highlight the importance of preserving scientifically valuable geological landmarks. Such efforts strengthen public appreciation for meteorite science, motivating support for ongoing meteorite recovery in research programs worldwide. In conclusion, the continued investigation and conservation of the Hoba Meteorite offer valuable opportunities for multidisciplinary scientific advancement. From improving our understanding of planetary formation and asteroid impacts to guiding practical applications in planetary defense and space resource utilization, Hoba remains an essential focal point of research in planetary science, geology, chemistry, astrobiology, and space exploration. Further research into the Hoba meteorite has also contributed significantly to planetary defense studies, particularly in developing more accurate predictive models of meteorite behavior during atmospheric entry. Scientists employ computer simulations incorporating Hoba's unique physical characteristics to refine calculations, impact prediction methods, and disaster preparedness strategies. Such predictive models assist international scientific communities and governmental agencies in assessing potential threats posed by near-Earth objects, NEOs, and designing effective mitigation approaches. The geochemical composition of the Hoba meteorite, specifically its elevated nickel content, provides critical clues into the formation processes of metallic planetary cores. Comparative analyses between iron meteorites like Hoba and seismic data from Earth's core help researchers better interpret Earth's internal structure, thermal history, and core mantle interactions. These analogies expand knowledge of planetary differentiation, a vital geological process determining the layered internal structures common among terrestrial planets, including Mercury, Venus, Earth, and Mars. Additionally, the corrosion and weathering studies of the Hoba meteorite offer a unique opportunity to observe how iron-rich extraterrestrial materials interact over time with Earth's atmospheric and environmental conditions. Detailed analyses reveal the progressive formation of iron oxide minerals such as magnetite, hematite, and goethite on Hoba's surface, demonstrating oxidation processes at varying depths and conditions. This information allows researchers to reconstruct past climate conditions and environmental histories of the region, linking meteoritic studies directly to Earth's climatological research. From an educational standpoint, the ongoing scientific interest in Hoba has encouraged numerous collaborative international projects promoting meteorite science education globally. Institutions worldwide frequently reference Hoba in developing educational curricula, outreach programs, and museum exhibits, significantly influencing public understanding and appreciation of astronomy and geology. Such international recognition fosters scientific cooperation, encourages student involvement in meteoritics, and increases public support for ongoing space science research. The discovery and detailed study of the Hoba Meteorite have also inspired advances in laboratory methodologies for investigating extraterrestrial materials. Advanced analytical techniques, including synchrotron radiation spectroscopy, laser ablation, inductively coupled plasma mass spectrometry, LICPMS, and high electron microscopy have been refined through analyses of Hoba-like materials. These advancements not only deepen scientific knowledge about the meteorite itself, but also broadly enhance research capabilities applicable across multiple scientific disciplines. Finally, ongoing efforts to preserve the Hoba Meteorite site underscore the importance of conservation measures in safeguarding rare geological and astronomical heritage. Recognizing its scientific, cultural, and historical value, conservationists, scientists, and local authorities have collaborated on protective strategies aimed at minimizing vandalism, natural erosion, and anthropogenic impacts. These preservation efforts set an important international precedent, highlighting the need for protecting scientifically significant meteorite sites around the world, thus enabling continued scientific access and public education for generations to come. In essence, the comprehensive exploration and preservation of the Hoba meteorite offer profound and wide-ranging implications across diverse scientific fields: planetary science, astronomy, geology, geochemistry, climatology, planetary defense, and astrobiology, making it not only the largest meteorite on Earth, but also one of the most scientifically influential extraterrestrial objects ever discovered. The Hoba meteorite continues to serve as the cornerstone for interdisciplinary scientific research, providing valuable data on planetary formation, impact physics, space resources, and terrestrial environmental interactions. While its sheer size and composition make it an extraordinary object of study, ongoing investigations have expanded its relevance to emerging fields such as space mining, planetary habitability, and long-term preservation of extraterrestrial materials. One of the critical areas of study involving the Hoba meteorite is its connection to planetary core formation theory. theories. Scientists hypothesize that iron meteorites like Hoba originate from the metallic cores of differentiated asteroids that were shattered in early solar system collisions. By examining the metallurgical properties and isotopic compositions of Hoba and other iron meteorites, researchers can infer how molten iron nickel alloys crystallized within protoplanets billions of years ago. The high concentration of nickel and trace elements like iridium and platinum in Hoba supports models suggesting that such metallic bodies experience slow cooling within large parent asteroids, similar to Earth's core formation process. Beyond geological and planetary sciences, Hoba has influenced the growing field of planetary defense. While its low velocity impact minimizes destruction, its size and mass highlight the potential risks associated with larger meteorites and asteroids. By comparing the structure and atmospheric entry characteristics of Hoba with other impact events, such as the 1908 Tunguska event and the 2013 meteor. Scientists have refined impact risk assessments. The study of Hoba provides insight into how different entry angles, velocities, and compositions influence an object's survivability upon reaching the Earth's surface. Hoba's unique preservation has also contributed to ongoing research in space weathering. Unlike most iron meteorites, which rapidly oxidize and degrade when exposed to Earth's atmosphere, Hoba has remained relatively well preserved despite being exposed for thousands of years. Scientists attribute this to a combination of factors, including its chemical composition, the regional climate of Namibia, and natural protective patina layers forming on its surface. The study of this weathering process helps researchers understand the longevity of metallic structures in space, with implications for the preservation of spacecraft, satellites, and lunar or Martian exploration equipment exposed to harsh extraterrestrial environments. Another emerging research field related to Hoba involves the study of microbial interactions with meteoritic materials. Scientists have discovered that iron oxidizing bacteria colonize meteorites over time, influencing their weathering patterns. Similar microbial processes could play a role in extraterrestrial environments, such as Mars,